Yes, recording has started. Please go ahead, Professor Miyamoto.
Yeah, thank you very much for kind introduction, Eric. I'm Goro Miyamoto from Tokyo University, Japan. It's my great pleasure to have opportunity to give this online lecture. I really appreciate the organizers of this online lecture, especially for Eric and Leo. So today, I will talk on the effect of crystallography on the phase transformation in steel. So before starting my talk, I'd like to acknowledge the Professor Tadashi Guruhara and Professor Yon Jejan and the many doctor and master students who involves in this research. So this is the microstructure of meteorite. So meteorite is a kind of huge single austenite crystal, and you can see the Wittmann-Stetten ferrite forms in this meteorite. And this Wittmann-Stetten ferrite form along a specific crystallographic plane. And many different orientation of Wittmann-Stetten ferrite is present in this single austenite, which means there is a variant. So understanding of crystallography is very important to control microstructure after transformation. Especially crystallography has strong influence on the boundary density and texture, and also strongly related to transformation mechanism. So in this time, I'd like to explain the background of crystallography, such as orientation relationship and variant. And I will talk on two different types of transformation. The one is diffusional transformation, and the other one is displacive transformation, such as martensite and bainite. So this is a typical ferrite microstructure formed from austenite. At relatively low transformation temperature, the Wittmann-Stetten ferrite forms, and shown in this figure. So those ferrite has the plate shift or needle shift in three-dimensional morphology, then grow along specific crystallographic plane. And at higher transformation temperature, the grain boundary ferrite or alloteriomorphic ferrite forms. So morphology of ferrite become more irregular. So crystallographic constraint become weaker in comparison to the Wittmann-Stetten ferrite. But crystallography is still important in this grain boundary ferrite formation. So a common feature between Wittmann-Stetten ferrite and alloteriomorphic ferrite is the nucleation at austenite grain boundary. So to start the talk on the crystallography, first I would like to explain the orientation relationship. So this is FCC crystal, and the cross-packed plane of FCC is 111 austenite plane. And this 111 austenite plane is parallel to the cross-packed plane of BCC, 110 or BCC plane. And also cross-packed direction of BCC and FCC are in parallel relationship. So this is well-known Kurzgesagt orientation relationship. And in Nishiyama-Wasserman orientation relationship, 100 BCC is parallel to 114 austenite. So they differ by only 5.3 degrees. So they are very close to each other. And actual orientation relationship between austenite and ferrite or martensite deviates from both orientation relationships. But usually the actual orientation relationship is closer to the case. So in this talk, I will explain based on case orientation relationship. Then as I is shown in the first slide, the multiple orientation of BCC phase forms in a single austenite grain are shown in this meteorite picture. So in this schematic, the BCC, those two BCC satisfy case orientation relationship. as represented by this pink bar. And there are three cross-packed directions in one austenite plane. So totally 6 variants satisfy case orientation relationship for one austenite plane. And there are 4 austenite planes in FCC structure. So eventually 24 variant can be formed in a single austenite plane. So this is called as the variant. So variant is important when we think about the grain refinement. So if the random variant is nucleated, so then the density of high angle boundary in the final microstructure will be high because the variant boundary is usually of high angle. However, if specific variant is selected in the nucleation stage, then those variants will coalesce in final microstructure, which causes the coarsening of final microstructure. So the understanding of variant or orientation relationship is quite important. And such variant is determined in the nucleation stage. And this is the energy change during nucleation. So energy change of nucleation is a function of chemical driving force and strain energy and interfacial energy. Strain energy and interfacial energy is a function of orientation relationship or variant. For example, the previous research evaluate the interfacial energy as a function of orientation relationship between austenite and ferrite. So interface satisfying case orientation relationship is the most stable. And this interface energy is much smaller than the interface with irrational orientation relationship. Therefore, the ferrite tends to hold near case orientation relationship with austenite in nucleation stage. But as we know, the ferrite is nucleated at austenite grain boundary. So this ferrite can satisfy near case orientation relationship with only one side of austenite, and the other side become irrational orientation relationship interface. But this interfacial energy differ variant to variant. Therefore, the specific variant tends to be nucleated. So this variant will have the relatively low interfacial energy for the opposite side. So this is one example of the orientation relationship analysis of grain boundary ferrite. The black region is previously austenite, and currently this is martensite. And the bright region is grain boundary ferrite. So the circle and triangle represent near case and non-case interface respectively. For example, this grain boundary ferrite holds near case orientation relationship with both sides of austenite. So we define the near case and non-case as the deviation angle from the exact case orientation relationship. And threshold is taken to be 5 degrees. So a part of grain boundary ferrite holds the near case orientation relationship with one side, and the other side is non-case. And this ferrite growing into non-case side. So this is the statistics of the analysis. About 3/4 of grain boundary ferrite satisfy case orientation relationship with at least one side of austenite. And a part of grain boundary ferrite satisfy the case orientation relationship with both sides. So according to that analysis, it is clear that grain boundary ferrite is surrounded by near case interface and non-case interface in many cases. So difference in orientation relationship means the interface atomic structure is different. In incoherent interface, the FCC structure change to BCC structure by random atomic jump at the interface. And this incoherent non-trace interface has more open space. That means interface energy is high and interface mobility is also high. And non-trace interface is easier for solid segregation. On the other hand, at semi-coherent interface, case interface, the FCC structure change to BCC structure by regular atomic motion along specific direction, which cause the shape deformation during phase transformation, which cause also surface relief. So semi-coherent interface has less open space, so interface energy and interfacial mobility is low, and the segregation tendency is also weak. So this is a general understanding between incoherent and semi-coherent interface, non-case and case interface. So we try to quantitatively differentiate those two interfaces by experiment. So first one is a measurement of interface mobility for case and non-case interface. So in order to quantify the interface mobility, we focus on the energy dissipation for the interface migration. So energy dissipation for the interface migration is a function of two components. The first component is energy dissipation by interface mobility, so which is proportional to the interface velocity and inversely proportional to the interface mobility. The second term is velocity independent term and related to the strain energy. So in order to quantitatively analyze this relationship, we measure the energy dissipation experimentally. So this evaluation is based on the non-equilibrium interface composition. So this is carbon content profile measured by EPMA. So interface carbon content deviates from equilibrium value. And this deviation convert to the energy in thermodynamic analysis. So delta G total can be measured experimentally. Then such measurement is performed at various interface velocity. And interface velocity is evaluated by simply the thickness change of ferrite as a function of time. So based on those measurements, it is possible to estimate the strain term and interface mobility term by a slope of this measurement. And this concept is applied for ferrite transformation in iron carbon binary alloy. So this is the grain boundary ferrite, allotrophic ferrite AF, and Widmer-Stetten ferrite. So this is grain boundary ferrite. And this grain boundary ferrite satisfies case orientation relationship with the left austenite and non-case interface at the right austenite. And this is the carbon content measurement, and the interface carbon content deviate from equilibrium composition. And in the case of Widmer-Stetten ferrite, this Widmer-Stetten ferrite satisfies the case orientation relationship. And deviation from the equilibrium composition become greater than the grain boundary ferrite. So such measurement is conducted at various holding time and various transformation temperature. And energy dissipation is plotted as a function of interface velocity. So the one important point of this measurement is the intercept of Widmer-Stetten ferrite is not zero, but about few tens joule per mole. So this means the formation of Widmer-Stetten ferrite involves transformation strain. But transformation strain for grain boundary ferrite is negligibly small. And this slope represents the inverse of interface mobility. So then interface mobility is evaluated and plotted in the lower figure. The blue is interface mobility of grain boundary ferrite, and red is the Widmer-Stetten ferrite. The measured interface mobility is much smaller than the value reported by Professor Hira, Witz, and somehow close to report by Zhu and Clearer. And as we expected, the grain boundary interface mobility of grain boundary ferrite is much larger than the Wittmann-Stetten ferrite. So those analyses suggest that the non-case interface exhibit the higher interface mobility and smaller transformation strain. So in iron carbon binary case, non-case interface is more mobile than the Wittmann-Stetten ferrite austenite interface. But the situation can change when we add alloying element, because interaction of solute element with interface is orientation relationship dependent. So this is a TTT diagram showing the transformation kinetics in iron 0.4 carbon steel and molybdenum added 0.4 carbon steel. So by the addition of small amount of molybdenum, transformation is delayed in ferrite transformation temperature range and bainite transformation temperature range. And returning effect is greater at higher temperature. I mean, in the ferrite transformation temperature range. And in order to clarify the reason of this retardation, the molybdenum distribution at the interface is analyzed using 3DAP, three-dimensional atom probe. So in this case, the transformation at 700 degrees, grain boundary ferrite forms, and this interface is non-case interface. And as you see, the molybdenum is accumulated at alpha gamma interface, as shown in this figure. So molybdenum segregation is significant at incoherent non-case alpha gamma interface, which means strong solute drag effect occur at non-case interface. On the other hand, by decreasing 50 degrees, the bainite transformation takes place. And this bainite has near case orientation relationship with austenite. And there is almost no molybdenum segregation at the bainite and austenite interface. So that means the solute drag effect on bainite and austenite interface is quite small. This is because bainite and austenite interface is more coherent interface, and the molybdenum interaction binding energy to that interface is small. So based on that measurement, we think like this. So in iron carbon binary case, non-case interface is more mobile than the benefic ferrite case interface, especially at high temperature. But by the addition of molybdenum, the solute drag effect on non-case interface is great. Therefore, the migration of non-case interface is significantly retarded by the addition of molybdenum addition. However, such retarding effect on transformation kinetics is small for benefic ferrite formation. So as a result, benefic ferrite structure can be obtained by even at the slow cooling. This is because the solute drag effect on non-case interface is stronger than the benefic ferrite and austenite interface. So this can be a reason why we use molybdenum to design the benefic steel. So crystallography is very, very important in the grain boundary ferrite formation. But it is also important in partitic steel. As you may know, the steel wire or steel cable used in the bridge is made from partitic steel. And this partitic steel is heavily drawn to make the steel cable. And in the production of the drawing, the partitic steel sometimes failed, like this picture. So this is called delamination. And one of the reasons of this delamination is the formation of grain boundary ferrite in partitic structure. So ferrite is, of course, a soft phase, then pyrite is hard phase. So during drawing, strain is accumulated to grain boundary ferrite, which causes the failure during drawing. But formation of grain boundary ferrite in hypereutectoid steel is quite unusual. So we analyze what happens in the formation of grain boundary ferrite and pyrite. So this is the microstructure in the early stage of transformation. This is prior austenite grain boundaries. And we see the grain boundary ferrite actually forms. But the other side of austenite transformed into pyrite. So this is a ferrite orientation map measured at the same place. As you see, this grain boundary ferrite has the exactly same orientation as the particle ferrite. So first, the ferrite is nucleated at austenite grain boundary. And this ferrite growing to grain boundary ferrite to left side, but the same ferrite grain transform into pyrite to the right hand side. So then in order to clarify what is the difference between those two cases, we analyze the orientation relationship between ferrite and austenite. So this is the same place as the previous slide. This grain boundary ferrite holds near case orientation relationship with respect to the austenite. However, this particle ferrite holds non-case orientation relationship with austenite to the other side. So orientation relationship is quite different between those two cases. So this is the statistical analysis of orientation relationship and the morphology of the transformation product. When the deviation from the case orientation relationship is smaller than 10 degrees, grain boundary ferrite forms. But at larger deviation, more than 10 degrees, the paralytic ferrite forms. So orientation relationship is a dominant factor to form grain boundary ferrite. And as I explained, in the nucleation stage, ferrite tend to hold near case orientation relationship with at least one side of austenite. So that's why the grain boundary ferrite is formed even in the hypereutectoid steel. So this is the schematic of the pyrite and grain boundary ferrite formation. At the non-case interface, the normal pyrite is formed. However, grain boundary ferrite forms at near case interface. And during thickening of this ferrite, the actually cementite layer is also formed, and cementite is thickened. So this is because the carbon is supplied from austenite to cementite by carbon diffusion in ferrite. So cementite and ferrite both thickens. So this is a kind of eutectoid transformation, but in non-cooperative manner at case interface. So such strange behavior is due to the difficult cementite precipitation at the near case interface. And possibly because the interface energy is low at near case interface, and solute diffusivity is also slow at near case interface. And those factors prevent the nucleation of cementite at near case interface. So quite similar phenomena occur in the case of alloy carbide precipitation. So in normal eutectoid transformation in steel, we get pyrite transformation. But when we add the alloy carbide forming element, such as titanium, vanadium, or niobium, the austenite transform into alpha plus alloy carbide. So this is other types of eutectoid transformation. And in this case, alloy carbide is nucleated at alpha gamma interface repeatedly. So then eventually, such a very peculiar alloy carbide distribution appears. So this is called interface precipitation. And carbide in rows parallel to alpha gamma interface is evolved. And those nano-sized alloy carbide is used to strengthen steel sheet used for automobile body parts. And in this case, the alpha gamma interface is the nucleation site for alloy carbide. So its crystallographic structure is very important to understand the alloy carbide nucleation. So in this case, we also analyze the relationship between orientation relationship and alloy carbide precipitation. So this is the Widowsett ferrite, and this is the grain boundary ferrite. So then we analyze orientation relationship. So this Widowsett ferrite satisfy near case orientation relationship and growing to near case side. On the other hand, this grain boundary ferrite hold near case orientation relationship with one side of austenite, but growing into non-case side. So then alloy carbide distribution is analyzed using three-dimensional atom probe. So in Widowsett ferrite, the number density of vanadium carbide is very, very low. On the other hand, the high number density of vanadium carbide is observed. And you may be able to see the alloy carbide, the rods, parallel rods in this way, like this. So this is the relation between number density of vanadium carbide and deviation from case orientation relationship. So as we see, the vanadium carbide density is quite low at near case interface. So situation is quite similar to the grain boundary ferrite formation in paralytic structure. So the understanding is similar. At the non-case interface, we have high density of vanadium carbide interface precipitation. So non-case interface is an incoherent interface. Therefore, interfacial energy is high. The interfacial diffusivity of vanadium should be fast, and non-case interface should be more favorable for segregation side for the vanadium. And those factors should enhance the vanadium carbide nucleation at alpha gamma interface. And for the segregation, we confirm the difference between near case and non-case interface experimentally. So this is the measurement of vanadium and carbon at the near case interface. So there is almost no vanadium segregation at the near case interface. On the other hand, when we analyze the vanadium distribution at the non-case interface, at even less vanadium addition, so clear vanadium segregation is detected. So such vanadium segregation should be one reason to enhance vanadium carbide nucleation at non-case interface. So the crystallography of the alpha and gamma interface is very important to understand the diffusional transformation. So then in the second part, I also want to explain how the crystallography influence the microstructure, martensite and bainite. So last martensite, upper bainite structure is important to produce high strength steels. And in this case, martensite or bainite, of course, satisfy near case orientation relationship. And there are 24 variants, as I explained. And the single austenite grain is subdivided by so-called packet. And the packet is the aggregates of brass with the same habit plane. So the habit plane is nearly parallel to the cross-packed plane in parallel relationship. Therefore, variants in the one packet share the same parallel relationship of cross-packed planes. And So this is the one packet. And this packet is further subdivided by several blocks. A block is the aggregates of mass with nearly the same orientation. So the last boundary is the low angle boundary, while the packet, block, and prior oscillating boundary is of a high angle. So in order to understand those hierarchical microstructure of multensite or bainite, the understanding of variant is important. And this table shows 24 case variant. And these variants are classified into or based on the plane parallel relationship. So we call it cross-packed plane parallel group, CP group. In one CP group, the parallel relationship between cross-packed plane is shared. And there are 4 1-1-1 plane in austenite. So then there are 4 CP group from 1 to CP4. And the other important the variant grouping is the Bain group. As we know, the FCC structure can change to BCC structure by the compression along O1 FCC direction and slightly expanding to the perpendicular direction. And there are 3 O1 direction in austenite, so there are 3 Bain variant. The important feature of Bain group is that it is strongly related to the misorientation. Among the same Bain variant, for example, variant 1 and variant 4, misorientation is small. On the other hand, misorientation between the intervein variant is larger. So Bain variant is related to the high angle or low angle boundaries. So then the variant structure of martensite is analyzed in this study. So this is the low carbon martensite, and this is high carbon martensite. In the case of low carbon martensite, the block and packet structure is clearly seen. And in the orientation map, the variant 1 to variant 6 forms together, forming a single packet. And furthermore, the single block consists of 2 different variants, which has a low misorientation. So CP group is dominant, and the low misoriented variant pair is favorably paired. On the other hand, at high carbon martensite, the packet and block structure is less visible, but variant 1 to variant 6 forms as a group. So CP group still dominant. But variant pairing slightly changes. So in this case, variant 1 to variant 2 are favorably coupled. Those variants have twin-related variant pair and have a high misorientation angle. And this is the variant structure of the low carbon bainitic steel. So we can change transformation temperature in the case of bainite transformation. So if this steel is transformed at relatively low temperature, 450, we obtain such kind of microstructure, including high density of high angle boundary. But at higher transformation temperature, the boundary density of low angle boundary is much higher. Then the variant structure is analyzed using the CP map and the Bain map. In those maps, the same CP variant or same Bain variant is described by the same color. So at low temperature, the same CP variant form as a group. Instead, at higher temperature, the same Bain variant forms together. So variant structure change by changing transformation temperature. So according to such kind of analysis, we can identify 3 different types of variant structure for last martensite and upper bainite. For the first type, this is the low carbon martensite. The CP variant is dominant, and low misoriented variant pair is favorably coupled. When we increase carbon content or bainite transformed at low temperature, the CP group is still dominant, but twin-related variant is paired. The bainite at high temperature contains the Bain group, and as I explained, the Bain group variant have low misorientation. Therefore, the boundary density of high angle boundary become smaller in this microstructure. So this is the kind of overview of the microstructure change with carbon content and transformation temperature. So this is martensite, and martensite becomes finer with increasing carbon content. So this is well known. And in this experiment, a part of condition is below MS temperature. So in these conditions, the martensite forms first, followed by bainite transformation. So microstructure change is not so straightforward. So I focus on these conditions. So this is bainite formed at 500 degrees. And with increasing carbon content, the bainite structure slightly finer. However, at 400 degrees, the bainite structure becomes coarser with increasing carbon content. So this is the opposite tendency to the martensite case. And also one peculiar observation is the formation of coarse bainite structure along prior austenite grain boundary. So I will explain later of this part. So in order to understand such the grain size change with carbon content or transformation temperature, we need to understand the transformation strain accommodation. So martensite and bainite is displacive transformation. Therefore, shape change should be involved. And if austenite matrix is soft, so then this shape change can be accommodated by the plastic deformation of austenite. So dislocation or other defect should be introduced in austenite. And this defect can be a nucleation site for the subsequent formation of martensite or bainite. So as a result, the same variant is nucleated by autocatalytic nucleation. Then low angle boundary will be created in this case. However, when the austenite becomes harder, so plastic accommodation becomes difficult. Then in order to reduce strain energy, the other variant is formed. So this is self-accommodation and frequently observed in the non-ferrous martensite, for example, or shape memory in alloys. So in order to understand such effect of autocatalytic nucleation or self-accommodation, the matrix strength is important. So we consider the effect of the matrix strength and also driving force. So as I explained, the soft matrix is favorable for plastic accommodation, and hard matrix induced the self-accommodation. And of course, driving force is another important factor considering phase transformation. The driving force for martensite is simply the undercooling from T0 until MS temperature, and driving force increase is increasing carbon content. But in the case of bainite, at same transformation temperature, driving force will be decreased at higher carbon content. because austenite is stabilized by carbon. So in order to clarify the relation between austenite strength and driving force and grain size, so we calculate those three factors. The austenite strength is calculated according to this paper, and driving force is calculated by thermocalc, and those values represent the average vein size measured experimentally. So different symbols represent the different transformation temperature. So in a given specimen, the driving force and austenite strength both increase by decreasing transformation temperature or multi-site transformation. And at same transformation temperature, but decreasing carbon content, the austenite strength is lowered and driving force increases. So in the case of multi-site, so with increasing carbon content, the driving force and austenite strength both increases. So then this is the iso vein size line. So as we can see, the vein size become finer at higher driving force and higher austenite strength as we expected. So such a concept can be used to design the refinement of martensite and bainite. And one important phenomena is the formation of grain boundary bainite. So at certain conditions, we observe very coarse grain boundary bainite as shown in this figure. So bainite is nucleated at austenite grain boundary. Therefore, this phenomenon is related to the variant selection in nucleation stage. So then we observe the microstructure in the early stage of transformation. So in low carbon steel, the strong variant selection is observed. So single variant is formed at this austenite grain boundary. And this austenite grain boundary is mostly occupied by single variant. So which form the coarse grain boundary bainite. And similarly, strong variant selection takes place at medium carbon steel. But in this case, the untransformed austenite between bainitic ferrite finally decompose into different variant. So the formation of coarse grain boundary bainite is suppressed. So variant selection is important factor to understand the formation of grain boundary coarse structure. So then the selected variant is analyzed based on those three rules. This is the variant selection rules reported by Professor Furuhara. And the first rule is related to orientation relationship between bainitic ferrite and austenite behind the bainitic ferrite. And if this bainitic ferrite follows near case orientation relationship, and this interface energy will be small. So this is favorable for the nucleation of this variant. And if the bainitic ferrite cross direction is nearly parallel to grain boundary, then more grain boundary area will be consumed. So this is also favorable for the nucleation of this variant. So this is the second rule. The third rule is transformation strain. So if transformation strain is parallel to grain boundary plane or slip system in austenite in the opposite side, so then the strain accommodation become easier by grain boundary sliding or plastic accommodation. So I do not explain in detail, but the result suggests the rule 1 is dominant at high transformation temperature, while rule 2 and rule 3 is dominant at low transformation temperature and higher carbon content. So in general, the control of variant selection is not so easy, but by chance, we found one possible way to control variant selection of ferrite formation. So this is the prevention of variant selection. So in iron manganese carbon case, the strong variant selection takes place, and single variant is formed from one austenite grain boundary. And coarse grain boundary structure forms in the final microstructure. However, when we add small amount of vanadium or sulfur, so which forms vanadium carbide and manganese sulfide, then variant selection is significantly weak, as shown in this figure. And in the final microstructure, the coarse grain boundary bainite is suppressed. So we do not analyze in detail of this phenomena, but we suppose there may be two possible mechanisms. The first one is segregation of vanadium and sulfur may change the variant selection behavior. The other other possibility is the nucleation of bainite at vanadium carbide or manganese sulfide. So the control of variant selection using such a long element can be the one promising way to control bainite structure at grain boundary. So let me summarize my talk. So in this talk, I explained the effect of crystallography on phase transformation in steel. And in the first part, I explained the diffusional transformation behaviors. Especially non-case interface is important because non-case interface have higher interface mobility and smaller transformation strain. But non-case interface is more favorable segregation site. And this non-case interface serves as a preferential nucleation site for cementite and alloy carbide precipitation. And in the second part, the martensite and bainite. So CP group and bain group become dominant depending on the transformation condition and also alloy composition. And the stronger matrix and higher driving force can define the grains of martensite or bainite because the autocatalytic nucleation of the same variant can be weakened by strong matrix and high driving force. So currently we evaluate the austenite strength based on the empirical equations, but that equation may not be so accurate. So we should improve the understanding of austenite strengths at high temperature. So this can be the future research direction. We think based on that result. So that's it. Thank you very much for your kind attention.